Hello everyone, my name is Isaiah Morris. I'm a junior chemical engineer studying here at Arizona State University, and today I'll be giving my talk on confined nanodiamonds and their thermodynamic stability, which was my project for this summer. So nanodiamonds in short are sp3 hybridized nanocarbons with a crystalline or diamond core, exhibiting a very high surface area to volume ratio. Now, the most common synthesis route is detonation synthesis. You can see a figure of which here on the right. It typically involves a blast chamber, some inert gas, a mixture of TNT and RDX, a diamond blend, and a little bit of water. Now, these nanodiamonds have been found to exhibit many unique properties, including but not limiting to their easy functionalization, which we'll get into a little bit more in a little bit, their low toxicity, as well as their high Young's modulus, increasing the micro-hardness of materials that these nanodiamonds are incorporated into. And stemming off of that, these spherical nanodiamonds with this 5 nanometer diameter, give or take, have already been incorporated into existing materials. And stemming off of that easy functionalization, this highly tailorable surface chemistry, it makes these nanocarbons easily incorporated within polymer matrices, including PDC precursors. But when it comes to forming a PDC, you have to think of that last step, that pyrolysis, the high temperature treatment. And if we are encapsulating a nanodiamond within this polymer matrix, then how will that affect the nanodiamond? Will the temperature affect it, if at all? Well, it does. And as you can see in the figure here to the right, you can see exactly how. Nanodiamonds actually exhibit thermal decomposition as you increase their temperature treatment. So you can see that the dangling bonds in amorphous carbon that sit on the surface of the nanodiamonds begin to reconstruct and form these sp2 bonds. And the sp3 hybridized hydrocarbons within the actual nanodiamond themselves begin to restructure as well and form this large sp2-like shell that you can see developing as we move forward through the right of the graphic here until we reach a nano onion or an onion-like carbon, which happens to be a 0D nanocarbon, just like many of these nanomaterials are. It is 0D because the core of the nanocarbon itself is 0D. The plane is infinite and there is no long-range bonding. Now, onion-like carbons are very different from nanodiamonds, as you can see here in the diagram. Yes, they do still have those structural properties that a typical nanodiamond does, but they are combined and complemented with the optoelectronic features of multi-layer fullerenes. And as such, these nanocarbons have been recently studied by Gabriela Mera as unique carbon phases in PDC composites. But it is important to note the interfacial interaction between the matrix and the nanomaterial, as the performance of polymer composites relies on such. And the thermodynamics of this interaction will be studied via oxide melt solution calorimetry alongside Alexandra Navratsky and her calorimetry team here at ASU. Now, it is important to know that these nanodiamonds are covalently bonded with the polymer matrix. They are not additives, they are not fillers. They become one with the system. This becomes a multi-structure system, if you will. And this covalent bonding yields to a greater dispersion of the nanodiamonds, essentially trapping them into little cages, therefore avoiding those effects of agglomeration and overcoming those van der Waals forces. And coming back to this idea of the functionalization, well, when you actually functionalize a nanocarbon, you end up improving that adhesive energy within that interfacial region, as well as enhancing the thermophysical properties. So, of course, the first logical step of synthesis would be to functionalize the nanodiamonds. So they were first oxidized in air, attaching mainly carboxylic acids to their surface, which then led us to a one-pot aqueous sol-gel process with the likes of tetramethyl orthosilicate, 4-way percent nanodiamonds, as well as methanol as a co-solvent. Now, upon hydrolysis and condensation in the presence of water, these zero gels were then obtained and pyrolyzed in an argon atmosphere. You can see the results of said experimentation here on the bottom of your screen. Now, there are a few pieces of data that I want to point out. For starters, the mass loss within the nanodiamonds themselves. As you can see here in this blue curve, there was around a 4% mass loss within the nanodiamonds, but that can be largely attributed to the loss of functional groups as well as water from the nanodiamonds themselves. Another important thing to note is the BET analysis, and it's the specific surface area of the zero gel and of the composite itself, as at room temperature, the zero gel was found to be relatively mesoporous, but its max surface area was found after pyrolysis at 900 degrees Celsius, as you can see right here, yielding a value of 562, which is rather large. But as you increase temperature and you slowly but surely continue to conduct the pyrolysis, you approach the glass transition state for nanocarbon silica composites, which is 1280 degrees Celsius, which at that point, once you pass that temperature, everything starts changing. And at first glance, you would look at these two values and say, okay, well, pyrolysis at 1300 degrees Celsius had a specific surface area of 42. So obviously that material would have to be more dense. And that's what I thought as well at first, but this couldn't be farther from the truth. As you pass that glass transition state, the glassy state silica becomes more viscous and more amorphous and expands. And actually these 0D nanomaterials end up attaching themselves to the surface of these large inflated silica molecules, actually causing macroporosity instead of mesoporosity. So it's not that this material is more dense, it is just that it has bigger pores instead of a bunch of smaller ones. Now, what makes these materials special? Well, for starters, the main thing is that they exhibit no carbothermal reduction reactions, which, looking at the chemistry and the material itself, there should be some. So obviously, the nanodiamond has to be having some sort of effect, and it is. For instance, when we talk about nucleation sites, I spoke earlier about how nanodiamonds have a very large surface area to volume ratio. Well, all that does is provide many, many nucleation sites for silica to crystallize on top of the surface of this nanodiamond. You also have to consider the mesoporosity, as when a material exhibits something as mesoporosity, it is essentially a bunch of interconnected pathways allowing for the diffusion of carbon monoxide and silicon monoxide gases to leave the material, as well as also at the same time hindering that direct silicon carbide bonds that form within the material itself, therefore suppressing those carbothermal reduction reactions. Another very important thing to note is that you can obtain many different encapsulated nanomaterials starting from one. Starting from one nanodiamond, you can thermally decompose that to obtain different nanomaterials with different properties. Like you saw the OLCs, the onion-like carbons, they behave quite differently than the typical nanodiamond. It's also important to note that we used sol-gel synthesis and not the traditional PDC method, whereas the latter involves a separate step for cross-linking, as sol-gel synthesis does it all in one fell swoop. And the synthesis should be feasible for any pre-ceramic polymer, where these composites will still exhibit that same strong synergistic effect of these confined phases. And the product will be a smart nanocomposite with multiple opportunities, especially in sustainability when it comes to energy storage and the uses in photocatalysis and such processes like that. But going forward, we know that these PDCs are energetically stable. What I want to know is why. We know we have this nanomaterial in this shell, right? Well, how is that interaction with that inner wall? And how does that change with chemistry and the temperature of processing? All in all, how different is the whole from the sum of its parts? And I am looking to measure the different energetics of reaction via oxide melt solution calorimetry and utilizing this thermodynamic cycle that you can see here on the right of first, dissolving the nanodiamond and then dissolving the matrix and then the confined nanodiamond in the matrix. And from there, measuring the different heats of solutions to find the heats of formation and what actually is the thermodynamic properties of that interfacial interaction between the nanomaterial and the shell and the silica shell itself. And how does the strength of this interaction change as you increase in temperature, as you change this nanomaterial? Will the interaction change? Now, these are answers that I hope to get to these questions under my continued mentorship with Gabriela Mera and Alexandra Navratsky and the support from PIRE. I do hope to fly to Darmstadt, Germany next summer to continue my research. And it comes down to the bigger picture, the synthesis, characterization, calorimetry, and interpretation. How we want to first synthesize these core shell nanodiamonds and then characterize them using various instruments and machines to differentiate them from other materials. And then we go on to the calorimetry and learning their heats of formation and how that actual interfacial interaction with the nanomaterial and the shell it's encapsulated in, how does that change as this nanomaterial thermally decomposes as you go from nanodiamond to bucky nanodiamond to onion-like carbon. And that leads back to that fundamental understanding, the learning of the why. Why does this happen? Why do these materials, why does this certain nanomaterial exhibit a stronger interaction? Because theoretically, the stronger the interaction, the higher the stability and the better the material. And that's what we're really looking for. I think a few acknowledgments are to be made. First off, to NSF and PIRE, I do very much appreciate them sponsoring my research for this summer, as well as Gabriela Mera and Alexandra Navratsky for putting in time from their respective locations in Germany and Arizona to help me truly understand and grasp what my research was and how I would actually get involved with polymer-derived ceramics within PIRE. And then last but not least, I want to thank the Materials of the Universe group here at ASU for helping clear up some of those concepts that I would say are normally skimmed over in more scientific articles, and helping clear up some of that for me along the way. That is the end of my presentation. I very much appreciate you all listening and paying attention, and I wish you all have a great day.